Hello, my name is Matt Rains, and this is the video for Group 1 of Lab 4. First thing we're going to do is create a new Fluent project, and then we're going to go to Geometry, change it to 2D Analysis, and then New Design Modeler. We'll let that load. So based on the dimensions from the lab, we've created a model of the flat plate inside the wind tunnel. So we're going to import that here, and then click Generate. And here we go. Here's our wind tunnel with the flat plate in the test section. So now we can just close that out and then open meshing. Alright, so here we are. First we're going to make our name selections. Click on the edge selector here. It's going to be velocity, inlet, outlet, all of our walls. And then we're going to have to select all sides of the flat plate here. Make sure the whole thing is selected. Looks good. Now we have that done. We can go to Mesh, Method. We're going to do triangles, and then go to Sizing. And then we're going to change this to 0.003. For the actual simulation data, we use 0.002, but for the sake of speed, we're going to use 0.003. So now we just go here, generate. And we look, boom, there's our mesh. Looks good. We can close this. And then update. Perfect, now that's done. We can go into setup now. Let's do double precision. 2 solver processes. Start. Here we go. First thing we're going to go is to models, energy to on, and then we're going to change it to the K epsilon, and then the enhanced wall treatment with the pressure and thermal effects. That should be good for here. We can double check that our fluid is air. Right, everything in here looks good. Close that. Next we're going to go into boundary conditions and then inlet. Here we go. And then for our lab, and then we'll go into this later. So for the inlet, it's going to be 4.709477 meters per second. So close this. So we put that in here, apply, and then we can go to reference values, compute from velocity inlet over the surface body, and then we can change enthalpy to 2700. That velocity should now be here. So everything looks good. We can go initialize now. Perfect. And then we can do 250 iterations. And let's calculate. So now it's finished calculating. Okay. So first thing, we can go into results, and then we can get that velocity contour with the vectors. All right, so we can go here, insert vector, and then we're going to do symmetry 1. Make sure it says here velocity. And then here we go. So we can zoom in right here over the flat plate. We can see that velocity as it curves. All right, you can see that boundary layer kind of forming. All right, slower velocities here, and then the velocity slowly increases until it's unaffected. So you can just take a photo of that, and then that'll be your velocity contour with the vectors. And so we can go back into Fluent. So now the next thing we need is going to be the velocity profile. So we're going to have to go into plots, XY plot, and then we can name this plot at 0.2 centimeters. So we're going to go into position on y-axis, change this to velocity, and then change the directions here. And then we're going to have to create a new surface. So we're going to create line, and then we can call this whatever we want. We can line 0.2. So based on the model, right, when we made the model, we measured the position of the start of the plate. And so if you go from that position, that coordinate, and then add the distance from the leading edge, then you can get your x. So if you look at this Excel file here, you can see that we have our positions and then our x coordinates for ANSYS for the purpose of the simulation. So for at 0.2 centimeters, we're going to put the x position at 0.0165. We can put x1 as also that, 0.165. For y1, or for, sorry, y0, we're going to put 0.001 meters. So that's so that we can start at the top of the plate, right, since the origin would be the middle of the plate. And then for y2, or sorry, y1, we can put 0.004. So the theoretical boundary layer is supposed to go up to 0.002. So we can go a little bit above that just so we can see everything. And then we can just create and then close. And then so when we're going to plot, we're going to click line that we just made and then just say plot. And then as you can see, we have our velocity. So if we want to see more, right, we can't see the profile very fully. We can create just a new surface, going to just name it something different, and then keep the same x plot, 0.0165, 0.0165, and then same thing here, 1, and then just increases. We can 0.01 this time, create, and then if we plot this, now you can see more of that profile as it goes up, right? That velocity is increasing as our position goes across the plate, and then it starts to line out, right? That velocity stops increasing and remains more steady. So if we want to export that, we're just going to go click write to file, and then just write to our computer. So we do the same process for everything else. So we can do same thing, plot at 8 centimeters. We're going to have to create a new line, right? Change everything back to the way we had it. New surface. Right now the x for this is going to be 0.0945. And then we can keep the y the same. Create. And then what did we call this? Line 8. Oh, we created it. That's all right. Here we go. Save and plot. Here we go. Here's our velocity profile. And then same thing, just write to file. And then one more. 16 centimeters. Same process for all of these. So once you get the position of the start of your flat plate in ANSYS, then it becomes very easy to create these, right? Same thing, this is going to be 0.1745. 0.001, 0.01, and then we can call this line 16 centimeters. Here. Oh. Looks like we have a little bit of flow disturbance. That could be due to the mesh being less accurate for the purpose of this video. For our actual results, when we did a finer mesh, the profiles all looked very smooth. And then same thing, you click write to file, and then you write that to file. So that is it for the simulation portion of the demonstration, and then now we can go into plotting the velocity profiles. Okay, so next thing we're going to have to do is to first plot the velocity profile, but with normalizing the velocity with the free stream. And then we're going to calculate the boundary layer thickness. So here we have our data points. This is for 16 centimeters. And then we have 8 centimeters here. And then we have 0.2. So go ahead and copy all these into your own Excel file. So I have them all copied here. And then on this page, I have all the positions that they correspond with here. And I'm going to go over why they're in different pages in a minute. So first thing we're going to do is find the free stream velocity. So you can do this by putting a probe in ANSYS, or you can use the velocity that you calculated based on the fan frequency. And then what we're going to do is normalize it by dividing all these velocities with the free stream. So if we go into here, right, here we have each velocity divided by that free stream velocity. Same thing as we go on. Right, so these are all the velocities that we're actually going to plot. So now if we go into this first page, you can see that we have the first few velocities right up into the boundary layer and all the positions, right? The positions that we got these from were here. Right, so we're just going to use the same positions that we exported from the original plot in ANSYS. So after we do that, we're just going to create a new plot, and I can do this so we can just really quickly demonstrate. So if we go here, whichever one you like, we can just do the scatter with smooth lines. Right click, select data, new series, we can do ANSYS. For the X data, we are going to be plotting the velocity over the free stream velocity here. So just select that. And then for Y, the position. And as you see, boom, here we go. So that's our plot. And then you just do that for all the other velocities here. And then do the same method for the lab and Blasius. And that is not, I think, a part of the video that we were supposed to do. But it's the same process. Once you find all the velocities, just divide it by the free stream velocity and then plot it. So for finding the boundary layer thickness for the simulation, the main thing we did is just to find the position where the velocity hits 99% of the free stream velocity, which is defined as the end of the boundary layer. So if we look at V over V infinity, as soon as this number hits 0.99, that would be the boundary layer. So for the first one at 0.2 centimeters, the flow jumps up to over 100% of the free stream velocity, likely due to the nozzle effect. Right, the flow is slightly contracted as it flows over the plate. So we can see here that position is at 0.00231. And for the cases here where the velocity never quite hits 99%, linear interpolation would be used between these two values to find a more accurate representation of where it actually hits 99%. So same with 8, we can see it's somewhere between these two positions. And then for 16, it hits 99 almost exactly at here, 0.0059. So we have here, it's just the results tabulated. So for positions along the flat plate, 0.002 meters or 0.2 centimeters, 8 centimeters, and 16 centimeters. We have the boundary layer thickness as 0.00223 meters, 0.00488 meters, and 0.00586 meters. So here's those. So pretty simple. Pretty much just looking at the data, finding when it hits that 99%, and then tabulating results there. So that is it for part A through C of the simulation.
I'm Kyle Niven. This is the second half of Group 1 Wednesday Lab 4 project. I'm going to take you through the second half of whatever this project. So we're using the same setup as previously shown. So let's get to it. So what we need to find is the wall shear stress over the top of the flat plate. So if we go and create a XY plot over here, and we change our, we need to create vertical lines off of the top surface. As you can see, I've made most of them here. I'm going to show you how to create a new one here at 0.2 centimeters, which is what the front of the flat plate is going to be. So we create a new surface line. I'm going to name it something I can know what it is. So 0.2 centimeters. The X value we're calculating off of the origin. So that value is going to be 1.65 or 1.065. And our height is going to be, I did about quarter of the, I did half of the top of it, so it is 0.038. So from the center line of the wind tunnel, about 0.38 to avoid getting close to the top wall. Most of those values are going to be 0 anyway. Actually, we're going to start at 0, and the y value here is going to be 0.38. And we're going to stay at the same spot. So we're creating a vertical line right off of the top of the flat plate. And we did that all the way along the length of the flat plate. And we did it, or I did it in 2 centimeter increments, other than at the front, which is 0.2 off, because we didn't want to put it at 0, because you get kind of funny readings at the very front of the flat plate. So you kind of give a little bit extra space. So once those are all created, in the XY plot, like I said, I've made them all in 2 centimeter increments all the way to the whole length of the plate. So our y-axis function needs to be changed to ball fluxes. As you see, we got wall shear stress here. And then we need to select all the lines here that I've created. I need to remove that line because that's an extra one I made. But we can save and plot here. And as you can see, it's kind of created this. At these max values is what the wall shear stress is. But if we're going to take all that and actually write it to a file, but just so you can visually see it here, that's kind of what it is doing with wall shear stress. But we would do a write to files and save it as XY file and pull it up in Excel. I'll show you a portion of that at the end after we get all that. And the one last thing we need to get, because we will use those wall shear stresses also to calculate the local skin friction coefficient. And the last thing we need to get is the drag force coefficient. And I created a little bit different from the first setup. The first setup, we just created the boundaries of the whole plate as just the whole plate. Separated the top of the plate from those boundaries, just so I can get an accurate reading off of the drag force off of just the top of the plate. So I can compare that to theoretical. So I've already done that. But to get the drag force, we go to report definitions. And we create a new report definition here, and force report and drag. Bring it up here, and as you can see, I've separated the top of the plate and the bottom of the plate. Bottom of the plate has the front edges on it, but the top of the plate is strictly just the top of the plate. So we want to do drag force, click top plate and compute. And it will pull a drag force down here. And then I would take that value, that is our drag force value, just across the top of the plate, and I put that into Excel, do all my calculations. So pop over to Excel really quick here. As I said, simulate drag force, and then we calculated the drag force coefficient from there, and then compared it to our theoretical drag coefficient here. And also calculate the Reynolds number that is across the whole plate. So as you can see here, we didn't even reach turbulent flow, so it's all underneath, it's all laminar flow. So, but like I said, with the wall shear simulation, once you get into an XY plot, you delimit it down to just the values. You're gonna get a bunch of zeros that you need to just take out, and then you'll get values, single values at the wall shear stress there. And then we just plotted them against the theoretical calculations too. Same thing with skin coefficient. So calculated the skin coefficient using the wall shear stress that we found, just so ANSYS didn't have to, or Fluent didn't have to normalize the skin coefficient, so. But made those calculations here all in Excel, made a nice plot for it, so. Those are the last three things we needed. So that's wall shear stress, skin friction coefficient, and our drag coefficient comparison. So thank you.